Hey everybody, welcome back to another lecture video in our biochem course. This time we're going to be looking at acid-base chemistry. Specifically, we're going to be taking a look at some buffers. Buffers play a few roles of biological importance outside the lab and in our bodies. And so we are interested in how buffers work so that we can better understand the role that some of the molecules in our bodies are playing. And also the conditions that are going to support life as we know it. Not every pH condition is acceptable for life, and so, and you may know ours is somewhere around pH of 7.1 to 7.3, something like that. And so we're going to talk about why pH matters, how buffers work, and a little bit about that acid-base chemistry that we're going to look at a little more in depth later when we're talking about mechanisms of enzymes or charge differences on side groups of amino acids. So to start off, let's talk about the importance of buffers. So we can ionize water to a slight extent, about 10 to the minus 7 molar, to form hydrogen ion, H+, or a proton, and hydroxide ion, OH-. And we measure the proton concentration of a solution with pH, which is the negative log of the proton concentration. If the proton concentration is 10 to the minus 7, then the pH is 7. We can easily measure the concentration, or the hydroxide concentration, with a parallel equation. The pOH is going to be the negative log of that hydroxide concentration, and we would call that the pOH. So for example, in pure water, dissociation of a proton will simultaneously, create a hydroxide. And if you don't believe me, if we take H2O and we ionize it, we get an H+, and we get the rest of it, the OH-. So same time, simultaneous. So the pOH of pure water is also 7. This means that the pH plus the pOH is 14. Now, because protons and hydroxides can combine to form water, a large amount of one will cause there to be a small amount of the other. So you're thinking, why is this the case? So in simple terms, if I dump 0.1 moles of H+ into pure water solution, the high proton concentration will react with the relatively small amount of hydroxide there is, whatever hydroxide there is in the water, to create water, right? Thus reducing the hydroxide concentration. Similarly, if I dump excess hydroxide, NaOH for example, into pure water, the proton concentration falls for the same reason. So this is how adding large amount of one will cause there to be a small amount of the other. Let's talk a little bit about acids and bases. Now, chemists use the term acid to refer to a substance which has protons that can dissociate when dissolved in water or come off. They use the term base to refer to a substance that can absorb protons when dissolved in water. And both acids and bases come in strong and weak forms. And I'm showing you a table here of some weak acids. Strong acids, such as HCl, completely dissociate in water. If we add 0.1 moles, if you don't remember what a mole is, it's 6.02, 10 to the 23 molecules. If we were to dump 0.1 moles of HCl into a solution to make a liter, we'd have a 0.1 molar solution of hydrogen ion, because HCl completely dissociates. And so whatever the concentration of HCl I had, that's the concentration of H+ that I have. That's not the case for weak acids. So in the strong acid situation, there would be no more strong acid remaining. All the HCl would be gone. And same with if we used a strong base. All of the strong base would be gone because it would completely dissociate. Now, weak acids are different, and bases, from their counterparts. When you add 1 mole of weak acid into water, only a tiny percentage of that weak acid actually dissociates. And you can kind of imagine that here. So clearly weak acids are very different from strong acids. Weak bases behave similarly except that they accept protons rather than donating them. And since we can view everything as the form of a weak acid, we won't talk about weak bases here. So dissociation of a weak acid is often shown as HA, um, dissociating into H plus and A minus. So let's take a second and talk about why there's a little bit of confusion around that. So students are often puzzled and expect that H plus should equal A minus because the dissociation equation shows each one of them coming from HA. And so I've put this on here for you so that it can clear that up. Essentially, the reason that these are not always equal to each other is because this only happens when pure water dissociates, right? Any other time, there's going to be hydrogen ions and hydroxide ions that are present in that solution. And they're going to react with either the H plus or the A minus to form salts or to form water. And so we have to calculate their individual concentrations independently. And so what we usually do is we figure out the pH, or we figure out how much hydrogen ion there is, and then we can usually use that in stoichiometry or a mole-to-mole ratio or something to figure out the other. So we're going to use the Henderson-Hasselbalch equation to calculate the pH, and you can see that here. This is the equation you want to know. We'll talk about what those terms are in a second, and what we're going to use a slightly different form of it too that doesn't have AC minus and HAC minus, but that just stands for the sort of the weak acid, and so it's sort of the dissociated acid with the negative charge, and then the main acid here. But we'll come back to that. You might wonder why we care about weak acids. You've never thought so much about weak acids when you were in Gen Chem. Usually, your instructor might have described them as buffers, and you probably dutifully remembered that buffers are substances that resist pH, but maybe you didn't exactly know how to calculate that or how to see that for yourself. And in Chem 1B, they do spend a good deal of time on this. So let's talk about UPS. No, not the United Parcel Service. Instead, think of UPS as a battery backup for systems called uninterruptible power supplies that kick on in the absence of a battery failure, or a power failure. So the laptop is a UPS for your computer, right? The battery for your laptop, if you don't have any directed power, if it comes unplugged, the battery keeps it going. Well, we can think of acids or weak acids as UPSs with certain pH ranges, providing or absorbing protons as needed. Weak acids thus help to keep the H plus concentration, and thus the pH, of the solution that they are in relatively constant. Let's consider the bicarbonate carbonic acid system. I have a titration of that for us here. All right, so let's consider this system. This shows what happens to H2CO3, so carbonic acid, as it dissociates. So adding hydroxide ions by adding a strong base, such as sodium hydroxide, will actually cause the solution to the acid in the solution to lose those H ions, those hydrogen ions, and those will react with the hydroxide to make water. And consequently, the concentration of H plus is going to go down in the solution, and the pH is going to go up. And this is going to be because we're adding a base to an acid, it's going to neutralize the acid. We kind of maybe remember that already. However, in contrast to the situation with pure water, there is a backup source here available in form of H2CO3. This is sort of that. So we were talking about how it's a UPS, right? An uninterruptible power source. Well, in regular water, if we had added sodium hydroxide, that would eat up all the hydrogens in solution. But in this situation with bicarbonate, what it does is it eats up some of the protons are taken away by the the protons are taken away by the added hydroxyl. They're partly replaced by protons from the bicarbonate ion, or the carbonic acid. So this is why it's a buffer. So there's already hydrogen ions floating around from just the dissociation of water, from the partial dissociation of the weak acid, right? So the weak acid, do I want to write it like that? No. Let's write it as HA. Dissociates into a little bit of this and a little bit of that. And also water does. A little bit of this and a little bit of that. So we add strong base. We add sodium hydroxide. Well, that's going to go in here and wipe out these guys. But what happens is this H2CO3 isn't completely ionized, right? So it provides more hydrogens. And so this is how it buffers the pH. This is why the pH doesn't change so drastically as if we were in pure water. In pure water, as soon as these hydrogen ions disappear, the pH spikes. But in our buffer system, as soon as those hydrogen ions disappear, more show up. And so that's the point. It resists the pH by releasing protons to compensate for those that get used up when reacting with the hydroxyl ions. And so I wanted you guys to also note that this is important, because we'll see there are charges on our biological molecules, and these charges can change depending on the pH. pH of solution will affect whether or not hydrogen ions, hydroniums, are there or not there, or charges are there or not there. And so that'll affect the folding of our proteins a little later. So we're going to come back to that. All right, so the Henderson-Hasselbalch equation is useful. It allows us to be able to predict the response of this H2CO3 system to changes in the hydrogen ion concentration. The Henderson-Hasselbalch equation defines the relationship between the pH and the ratio of bicarbonate to carbonic acid. And so let me see here. I want a blank slide. Let me get us a whiteboard. Okay, so I'm going to write down the Henderson-Hasselbalch equation. So we've got pH is equal to the pKa plus the log of, and I said this is going to relate the pH to the two concentrations, the concentration of the bicarbonate, the HCO3 minus, and the carbonic acid, the weak acid. Okay, so this simple equation defines the pH as a ratio of these two concentrations, bicarbonate and carbonic acid. So the new term here is called the pKa. It's defined as basically being the negative log of the Ka, where the Ka is the acid dissociation constant. And the Ka is what we would get by just looking at how an acid dissociates. So a Ka, if we follow this all the way down the rabbit hole here, HA concentration, A minus concentration, all over the initial concentration. So it's a measure of how much the weak acid has actually ionized. And so that's what the Ka is. So the stronger the value of the stronger the acid, the more protons will dissociate from it when added to water, the larger the Ka value would be. Large values of Ka translate to lower pKa's, and as a result, the lower the pKa value, the stronger the weak acid is. So just how a lower pH means it's more acidic, a lower pKa means that these weak acids are stronger. Now, pKa's are constant. Okay, so for a given acid, the pKa is constant. The pKa for carbonic acid, for example, is 6.37. By comparison, the pKa for formic acid is 3.75. So formic acid is therefore a stronger acid than acetic acid. Acetic acid, than carbonic acid, sorry. A stronger acid will have more protons dissociated at a given time than a weaker acid. So how does this translate into stabilizing pH? So figure 1.35, which is this one, is showing us a titration curve. So this curve, the titration begins with the conditions at the lower left, very low pH, okay, because biological molecules can, in some cases, be exquisitely sensitive to changes, as in the pH. When the pH changes, the charges on the molecule change, and so you can see that. The pH goes up. So as we start to add sodium hydroxide, the pH is starting to go up correspondingly. And the amount of H2CO3 carbonic acid goes down. And so we can see in red here, or orange, carbonic acid, the amount of it is actually, well, actually we don't see the amounts here. We just see that it's converting into HCO3. And at this little point right here, this middle zone, this is when the ratios are equal. So it's called the inflection point. This is where half of the amount of my H2CO3 has been turned into HCO3. And so I have, at that point right there, which is essentially the pKa. We'll talk about what the pKa means or how it's calculated later, or at least how it's calculated for amino acids. But we get it. It basically means that there's a ratio of the HCO3 that's equal to the H2CO3. So a ratio of 1. So at that point right there, the ratio of these two species is equal to each other. And remember, going back to the Henderson-Hasselbalch equation, the pH is a measure of when or what these two concentrations are. It's a ratio. So when the pH is, or when these guys at the inflection point are equal to each other, then this is equal to 1. And we'll talk about the significance of that in a second. Okay. So you can see here, as we add more hydroxide, the H2CO3 starts to, it's decreasing. We can see the pH is going up, right? Because the amount of the acid is going down. And then it kind of flattens out a little bit. And it flattens out near the pKa. Now this is called the buffering region. Now the flattening of the curve tells us that the pH is not changing much. It's not going up fast, right? As it was earlier, when the same amount of hydroxide was being added. So for the amounts of hydroxide being added, the change in pH is much lower. You'll notice that the system is resisting a change in pH for about 1 pH unit above and below where the pKa is. This is the buffering region of the carbonic acid bicarbonate buffer. It's from about 5.37 to 7.37, and it's the strongest at 6.37, right there in the middle. So it starts to become apparent now how buffers are working. The HA, the weak acid, can donate protons when extras are needed, such as when hydroxide is being added to the solution. Similarly, A- can accept protons when extra hydrogens are being added to the solution. We didn't look at that situation, but if we were to just turn this around and start adding amounts of H+, we'll actually start to convert this H3O- back into H2CO3. And so it would be absorbing those hydrogens, again, trying to keep the pH from changing. So the maximum amount of ability to either donate or accept comes from when these two are in equal amounts, so when the ratio of them is 1. And this is consistent with the Henderson-Hasselbalch equation. When we actually go and plug in a log of 1, take you back to the equation, if we go in here and plug in 1, well, log of 1 ends up being 0. And so the pH is just equal to the pKa when these guys are essentially equal to each other. If we go back and look at the titration curve here for carbonic acid and bicarbonate, we see the pKa occurs right here at the pH of 6.37. So a pKa is related to a pH in that it's when there is an equal number of our, let's say, weak acid and its conjugate base, or the two conjugate, whether they're acids or bases, when they're in equal amounts, or when 1/2 of the starting acid has been converted into its weak base component. Okay, so for any buffer, a buffer will have a maximum strength and display the flattening of its titration curve when A- is equal to HA and when the pH is equal to the pKa. If a buffer has more than one pKa, and I do have an image to show you, some acids have more than one pKa's, and some of our amino acids are also going to be the same way. Then each pKa region will display its own sort of buffering behavior. So you can see here, this is aspartate, it's an amino acid. It actually has one to 3 pKa's, so 3 different regions in which it'll buffer. Okay, so let's talk about buffered versus non-buffered. To understand how well a buffer protects against changes in pH, let's consider adding, let's consider to 1 liter of pure water. So, if we were to add, excuse me, 0.01 moles of HCl to 1 liter of pure water with no volume change at a pH of 7, compared to adding to 1 liter, so this is pure H2O, and let's say this is also 1 liter of a buffered solution, let's say a 1 molar acetate buffer solution. So acetate would come from acetic acid, so this has a buffer at about, this has a pKa at about 4.76. So since the HCl completely dissociates, in the water, this is going to be, let's see, 0.01, so 10 to the minus 2 molar. So we would have to look at the pH, so negative log of that. The pH would go from a 7 to 2. Big difference. Now, in contrast to that, if we look at we do the same calculation, we're going to see 4.76 pH dropping to about 4.74. So buffered versus unbuffered gives us a very big protection, right? Having a buffer in there for just a small amount of HCl is going to make a significant difference. Let's talk about buffer capacity. It's important to note that buffers have capacity limits, limited by their concentration. Let's imagine that in this previous example, we had added 0.01 moles of HCl to the acetate buffer, but the acetate buffer only had a concentration of 0.01 molar, right? And so then at that moment it has equal amounts of, let's say, the acid and the conjugate base. And when we try to do the math, we see that we add, let's see, so many protons. Sorry, if this is the concentration of the acid, then at the maximum buffer capacity, the acid portion of it and the conjugate portion are going to be in equal amounts. Both of these will be 0.005. So just to get my example straight. So if I don't have a buffer that's big enough, if I have a concentration of a buffer that's 0.01, and I'm using it when I have, the maximum buffer capacity, meaning these two species are in equal amounts, giving me the widest buffer range, then I add 0.01 molar of HCl, I'm going to overhit my buffering ability here. And what we'll see then is that while half of the protons I added got absorbed, half of them would still be unbuffered. And if we take half of those unbuffered, so let's say half of 0.01 is 0.005. If this is my my hydrogen ion concentration, well then the negative log of that is going to give me something like 2.3. So 7 drops down to 2.3, or 4.76 here drops down to 2.3. So we're going to get a big change, again, if my buffer capacity isn't large enough. So you want to make sure that the concentration of the components of your buffer are actually big enough to accommodate the amount of acid or base you're adding. Okay. Let's talk about multiple ionizable groups, because amino acids have these, and we need to talk about them. So what happens if a molecule has 2 or more ionizable groups? Well, as it turns out, not surprisingly, each group has its own pKa, and each group has its own buffering region. So you can see here aspartic acid. Note that instead of a single flattening, we see 3 such regions. Each of these buffering regions is centered around their respective pKa value for the carboxyl group and the amine group. Aspartic acid has 4 possible charges. It has a +1 charge at low pH, and so the charges that we're looking at are found up here on the molecule. Okay. So a +1 charge at low pH because the 2 carboxyls are protonated and uncharged, and the amine group is actually protonated and charged. And so as we move down the line here, we see that this next particular iteration of the molecule, one of the pKa's has passed, and so our carboxyl group has lost its hydrogen, gaining a negative charge. Now the charges are equal, and we'll talk about what a Zwitter ion is. A Zwitter ion is when a molecule has no charges. I'm sorry, when a molecule has no net charge. It's also known as the pi point, the point where the charges are balanced. If we keep increasing the pH here, we'll see that the second pKa happens. The second most acidic part of this molecule will lose its H, giving it two negative charges and a positive charge, so a -1 overall. And the amine groups tend to be the least acidic, and so they have the highest pKa's. Eventually, though, if you hit pH high enough, the amine group loses its H, losing its positive charge, and we're left with a -2. So, changing charges. Now, how does one predict the charge for an amino acid at a given pH? A good rule of thumb for estimating charge is that if the pH is more than 1 unit below the pKa for a group, carboxyl or amino, then the proton is on. If the pH is more than 1 unit above the pKa, then the proton is off. If the pH is not more than 1 or less than 1 pH unit from the pKa, then you can't do this assumption. And again, it's just an estimate. Okay, there's a pi point, the pH at which the charge of a molecule is 0. That's the exact value calculated as the average of the two pKa's, and it's calculated from for each different amino acid. So here you can see that the pi point, where the charge is actually 0, is right here at a pH of can we tell? Doesn't really say. But it's an average of the 3.86 pH for the pKa2, the 2.1 pH for the pKa1, and so the pi point is that calculated from those two pKa's. Now this one would have, every amino acid is going to have slightly different values of pKa, so each of these pi's would be different. But again, you could look at the pi, and if you are above or below the pi point, you know that the charge is changing, or at the very least you know that the charge is 0 at the pi. Okay, again, trying to estimate the charge of an amino acid, I'm going to show you a little table later. Of course, there's one in the book as well that will just tell you what the charge on the R groups are. But when we get to proteins and amino acids in the next lecture, we'll look at that. All right, so I think that was the end of that one. So email me if you have questions. We will pick up with the next lecture, and I will see you guys next time.